And
Doing okay. Setting up the old screen sharing.
that whiteboard behind you looks like the Big Bang Theory.
I like the sort of like palimpsest theory of using the whiteboard, where you just keep adding stuff on top of other stuff. In some way, this is a lot of what we're going to talk about today, but I can't find my little wipe, so that's just how it's going to have to be. It's more of a shield, so you can't see the rest of the kitchen anyway.
Is that right?
Oh,
you're shielding your family from opprobrium,
yeah,
from quantum opprobrium.
Where's the? Oh, here we go. Participants. Alrighty. So yeah, let's get started. We're just gonna pick up where we left off. We were, kind of in the middle of a whole bunch of great stuff. Yeah, specifically right here. Today we're gonna get kind of into the nitty gritty of the Majorana polynomial representation of spin. And, in doing so, I want to emphasize, something like when you just consider an isolated quantum system, and I'm not going to say every quantum system, but at least in the case of spin, superposition should not be that mysterious. We've seen in the case of the qubit that, a superposition of up and down is really just the guy pointing in the x direction. The trickiness and the bizarreness, the weirdness, it all comes in once you start considering measurement, entanglement, multiple. So, that's where we'll be leading up.
Didn't hear your last ideas because there was some kind of noise interference.
I hear that too. All the weirdness, so to speak, comes in once you start considering measurement, entanglement, multiple quantum systems, and that's where we'll, end up. But before we get there, let's dwell a little bit more on exactly how this representation of spin works. And we'll see that, you can regard it as something of a classical system. All right, let me make this a little bigger. So, we've talked a lot about, the complex projective space that we use to represent a qubit. And when you think about it, there's already an analogy there to polynomials, in the sense that if you have a monomial, a polynomial with a single root, that root is invariant if you multiply the polynomial by a complex number. And so already that's kind of like our complex, projective representation of a qubit, where you can multiply by any complex number. If it's normalized, we're talking about multiplying it just by a phase. It represents the same state, represents, all the probabilities will be the same. So, is that more than an analogy? So, considering the case of, suppose we have a single root, we can consider a monomial that has that as the root. So, for example, if we had a root alpha, then the polynomial with that root would be z minus alpha. And so the first thing to note there is that for the polynomial representation to work, we got to stick this minus sign in there, because you gotta move the alpha to the other side of the equation. Simple as that. But when we come to considering, you know, a root at infinity, which is supposed to be, say, a point on the Riemann sphere at the North Pole or the South Pole, depending on your choice of stereographic projection, you have a problem. Because, you know, we said, well, okay, so, you know, if we have a complex number alpha, we want to, you know, send it to a little 2-vector 1 alpha, then what we said was, you know, if alpha is infinity, we should send it to the vector 0, 1. But if we interpret that as a polynomial, then it has no roots. You see here, you know, you plug in, say, 0 and 1, and there's nowhere where this guy equals 0 because there's the constant term. So, you know, you think, it's not going to work. But the trick is to reinterpret this as the polynomial has a root at infinity. And this will work for degree n polynomials. Whenever we lose a degree, we're going to add a root at infinity. And so you can think about this like, you know, a polynomial in itself could have, you know, if it's, you know, like the Taylor expansion of like sine or something like that, it could have an infinite number of terms. If you want to confine yourself to working with like a finite dimensional vector space of polynomials, there's a sort of question, which is like, so you have a polynomial like a z to the third plus b z squared plus c z to the first plus d. But, you know, what if alpha, a and b were both 0? This would reduce down, you know, to a degree 1 polynomial. In other words, the polynomial itself doesn't keep track of like the dimensionality of the vector space that we want it to live in. And so we have this rule, which is that if any of these like higher power coefficients are 0, then we add these roots at infinity. And that allows us to keep track of, in a way, the dimensionality of the vector space, so that any polynomial in this vector space can be associated uniquely with some roots. If that
Matthew, I'm confused here. A root is a solution to the polynomial. I don't understand what you mean by a root at infinity. You mean that z equal infinity is a solution to the polynomial?
Yeah. And that seems weird when you're talking about, you know, this kind of polynomial. So like this example here, right? F of z equals, you know, just 0z times minus, you know, 1. If you plug in, you know, that will never be, you know, you ask, you know, where is that 0? What's the root? And you get -1 equals 0. You know, it doesn't make any sense. So literally speaking, just from that, no, you know, it doesn't have a root. But we're going to sort of extend our idea of the polynomial, and we're going to say it does have a root. And you might wonder, is that justified? You know, does that make any sense? It's consistent, you know, what I said, in the sense that, you know, you could just keep track of the higher terms that you've lost by adding roots at infinity, but there's a sort of a more systematic way of thinking about it. And that's—
Well, Matthew, you know, everybody knows that -12 equals infinity. That's been proven.
The Riemann zeta function.
Isn't it -1 over 12?
Oh, maybe that's what it is. So -12 equals 1 over infinity. No, that's not right.
I think it's 42. It's supposed to be 42.
42 sounds good to me.
You haven't seen 42 in 25 years.
Are we leading to spin, the theory of spin? Is that, we're going to get the spin eventually from this?
Yeah.
Oh, okay. Okay, good.
So the more systematic way of dealing with these roots at infinity, is instead of working with a single variable polynomial, to work with a 2-variable polynomial. specifically, if we had a single variable one, we would homogenize it. In other words, we would add another variable w, and we would make sure that the degree of each term is the same. So, for example, if we had just a single variable polynomial, f of z equals c1z plus c0, we would upgrade it to a two variable polynomial, f of wz, where now there's a little w there, multiplying the c0. And here's how you can think about it. It's like, if we want f of wz to have a root 1, 0, that's just saying we want, when we plug in 1, 0 into that polynomial, we want 0 to come out. And so we could get that. We take 1z plus 0w, which is just z. That has a root when z equals 0, and w can be anything. If we want f of wz to have a root 0, 1, in other words, we want f of 0, 1 to be 0, then we could use the polynomial 0z plus 1w, aka just w, which has a root when w equals 0 and z can be anything. So we have it that a z root lives at the North Pole and a w root lives at the South Pole. And so, this is like sort of equivalent to what I said about using a single variable polynomial. And every time you lose a degree, you add a root at infinity. This is doing the same thing. So, the former made you a little uncomfortable, you can use this method. Furthermore, you sort of have to consider the sign, as I was mentioning, right? So if you have some f of wz and you want it to have a root at 2, 3, then you want the polynomial 2z minus 3w. In other words, you got to put that minus sign in there so that when you plug in 2, 3, you get 2 times 3 minus 3 times 2 equals 0. So in other words, if you want a homogeneous polynomial with the root c1, c0, then you should use the polynomial c1z minus c0w. What we can do now is consider the case of higher degree polynomials. And in the spin case, this turns out to be considering not just the spin half case, which is familiar in the normal block sphere representation as just a point on the sphere plus a phase. Now we can consider arbitrary spin j states. And similarly to the case of the block sphere, we can represent the spin j state as not just one point on the sphere, but as a constellation of points on the sphere. And the points are given by the roots of the polynomial. So, to wit, a degree 1 polynomial will represent a spin half state. A degree 2 polynomial will represent a spin 1 state. Degree 3 polynomial will represent a spin 3 half state, and so forth. And this is like kind of cool. Like, it works because of the fundamental theorem of algebra. But geometrically, it's kind of awesome. You know what I mean? It's kind of surprising, right? If you have a spin, sorry, this should be a spin, not just 2j. If you have a spin j state that's normalized, it lives in 2j plus 1 complex dimensions. You think about those as real dimensions, it's 4j plus 2 real dimensions. Therefore, it represents a point on a 4j plus 1 sphere. And we can represent that as a unique constellation of 2j points on the 2 sphere. So it's this sort of surprising fact that, due to the normalization condition, you can have this, n-dimensional complex state that represents, some spin j something. And it represents a point on some higher dimensional sphere, as I say, due to the normalization condition that, the length of the vector has to be 1. But you can actually, there's a complete, representation of it as just 2j points on the 2 sphere. All those higher dimensional spheres kind of collapse down to just the 2 sphere. And, Majorana, the Italian physicist in the 30s, was the first to apply this, at least in the case of spin. This sort of technique had actually been known already to Maxwell, arguably. and other things. Okay, so just working through some examples, just so we get like the feel of this. Suppose we want to consider a spin one, in this case, a degree.
Hey, I'm sorry, Matthew. What was known to Maxwell?
So, Maxwell introduced this idea of like multipole vectors, which, was a way of describing, now I haven't read the paper, so I don't know the full details, but, essentially using, a series of unit vectors specifying directions at a point as a way of encoding information about the electromagnetic field.
So this would have been interpreted as polarization rather than spin. It was because Maxwell had no conception of spin.
Yeah, that's an interesting point. Yes, certainly, Maxwell wasn't using it in the context of spin. That was left for Majorana.
Oh, polarization would be the physical interpretation.
Maybe so. Yeah, I haven't. I picked up a reference to this in another paper, and I haven't really worked it through myself, so I can't totally confirm that. Just to say, Majorana didn't completely dream it up, late one night. So suppose we want a polynomial with two roots at 2, 3. Again, that's not a normalized spinner, but whatever. So you would just do, 2z minus 3w squared. You work it out, and you get, this polynomial 4z squared.
Matthew, I guess I would like it. You were starting before Michael asked you that question to start this conversation with a physical spin system. Can you go back and do that? How's 2, 3 relate to the physical spin system?
So 2, 3 is going to specify a point on the sphere. And now we want 2 points on the sphere. In this case, 2 points at the same point, both at 2, 3. And remember, to get the point on the sphere, you do, 2 over 3, and then stereographically project from the plane to the sphere. So what I want to emphasize here is, what are our basis vectors in this space of polynomials? So for example, if we want a polynomial with 2 roots at 1, 0, that turns out to be z squared. We want a polynomial with 2 roots at 0, 1, then we want w squared. If we want a polynomial with 1 root at 1, 0 and 1 root at 0, 1, in other words, 1 root at the North Pole, 1 root at the South Pole, then we want the polynomial zw. And these give us our basis states. You see, so I can, just write any polynomial as like a linear combination of...
Matthew, I think I lost you here. You said that z square has 2 roots at 0 and 1?
2 roots at 1, 0, where you see I'm taking that 1, 0 and I'm plugging it in for w and z there. Now note, the order of this, f, it could have been f of zw, but it's actually f of wz. We'll come back to why I made that choice later. But the idea is that if you have one of these little 2-dimensional vectors, then you plug 1 in for w and you plug in 0 in for z. And the question is does that make the whole polynomial go to 0? Is that a root? So you see here, it does, because, you plug 1 into w, and, whatever, doesn't matter, there's no w in the equation. You plug in 0 in for z, and yeah, it's 0, and it has multiplicity 2. Similarly for this one, the zw has a root at 1, 0 and 0, 1. If we plug in, w equals 1 and z equals 0, then it's 0. If we plug in 0 into w and 1 into z, then it's also 0. So, I just made this little chart. It's like we can write any homogeneous 2-variable polynomial of degree 2 as a linear combination of z squared, zw, and w squared. These, basis polynomials have these roots considered homogeneously. And if we want to work with the complex number infinity representation, like if we just want to work with the single variable representation, you can see that, instead of using 0, 1, we can use infinity. So what's interesting, right, is that like, due to the fundamental theorem of algebra, any two-starred constellation can be written as a complex superposition of these three constellations. 2 stars at the North Pole, 1 star at the North Pole, 1 star at the South Pole, 2 stars at the South Pole. All you do is find the roots of the polynomial. In order to get consistency with the usual representation of spin in terms of a JM vector, in other words, normally we represent spin where we pick a J value, whether that's 0, a half, 1, 3 halves, could be an integer or a half integer. And then the different basis states are given by the M value, right? So for spin half, the M values are a half and negative a half. For spin 1, it's 1, 0, and negative 1, and so forth. Given such a vector, such a state representing a spin, how do we find the corresponding polynomial? Like we worked it out in the case of just a monomial, where we had to recall with that little minus sign issue. So suppose we have, so how does that play out in the case of a degree n polynomial? If you have a JM vector, say here, I've just written the components out, A0, A1, A2. If you want the polynomial whose 2j roots correspond to the correct points, taking into account the negative signs, you use this expression, and this is the famous Majorana polynomial. In other words, you see that you take the components of this vector and they end up weighting powers of z. There's a little -1 term here so that, when I is 0, goes from I equals 0 to I equals 2. This is gonna flip the sign of like every other term. And then we have this little like normalization guy for each component, which is the binomial coefficient. And this will work. Now, why does it work? Okay, so the minus sign perhaps makes sense because it has to do with the as we saw up here. If you want where was it? Yeah, if you want alpha to be a root, you got to put a negative sign there. Otherwise, you get minus the root. Why does the binomial coefficient come into play? And ultimately, I won't go into the full, thing at the moment. You'll see a bit more intuitively later on. But if you think back to Vietta's formulas that relate the roots of a polynomial to its coefficients, we saw that, the coefficients are like, the sum of all the roots. And then like the sum of the roots taken pairwise and multiplied together. And it's like the sum of the roots taken like 3 at a time, multiplied together. And it's the sum of the roots 4 at a time. And so the number of terms in each of those formulas is just given by, the binomial coefficient. And so you can think about it like when we go from a polynomial to the JM representation, we're normalizing each coefficient by the number of terms that contribute to that coefficient in Vietta's formula.
But Matthew, isn't this limited by the dimensionality? I mean, you can't solve a polynomial in closed form beyond 5 dimensions, can you?
So yeah, so like you're gonna approximate the roots, So, yeah, but
So this is an approximation?
Well, I mean, it's not an approximation. It's like if you want to know the roots, you have to do an approximation. So, so I have some Python code here, which implements this. We have a little function that, does our stereographic projection. We have a little function that, keeps track of, what we said about infinities and losing degrees.
Will Python constrict around the root?
Well, it's interesting. There's a sort of, an interesting point about, if like you integrate around a root in the complex plane, something interesting happens. I don't know. I was reading about that last night. Anyway, so, all right. So what this does is, in a way, this jumps ahead a little bit. Qtip, the Python library that I use, has in it representations of the Pauli matrices, XYZ, in any dimension, right? So there's going to be XYZ matrices that will rotate a spin half representation, a spin 1 representation, and so on. We'll see later on how to calculate those matrices, but we're just going to take it for granted right now. And what we're going to do is we're going to look at the eigenstates of X, Y, and Z for a given J value. And what you'll see is, so for example, if we have spin 3 halves, and maybe I'll just run these guys in the old terminal. I have to say, as much as I love the Jupyter Notebook, I find it, very inconsistent in terms of running things at any drop of a hat. All right, so what I did was I chose, say, spin 3 halves. Okay? I got the Pauli XYZ matrices in that dimensionality. And then I found the eigenstates of each of those matrices. And then I used Majorana's polynomial to convert that JM state into a polynomial, and I found the roots. And what you get here is, okay, so the first column is X, the X eigenstates. So, at the top row, it's, the 3 halves state. And then the second row is the half state. The third row is the negative half state. And the bottom row is the negative 3 halves state. And the first column is the eigenstates of X. The second column is the eigenstates of Y. And the third column is the eigenstates of Z. And you can see that they have sort of the form that I promised you, which is that if we, remember in this thing, X is sideways, Y is up and down, and Z is going into the page. And now you can't, because some of the roots are in the same location, it's maybe perhaps a little hard to see here, but the idea is that for X, say, the highest weight state has 3 stars in the X plus direction. And then the next highest state has 2 stars in the X plus direction, 1 in the X minus direction. And then the next has 2 stars in the X minus direction, 1 in the X plus, and then finally all the stars in the X minus direction. Similarly for the eigenstates of Y, it's the same pattern, but just in the Y axis, and then same for the Z. Now, if you're worried about the fact that we have these, you can't tell, are there 3 stars at that location, or it looks confusing, I have here written out, it calculates the stuff. So, Yeah, let's look at the Z eigenstates because it's easiest to see.
Is this all original programming?
Yeah, I programmed it myself. I mean, again, none of this is like original mathematics.
But this must take you forever to do.
I mean, to me, it's how I understand it. You know what I mean? It's like, I don't pretend that I understand it until I can write a Python program that calculates it. So, considering, you know, say like the highest weight Z eigenstate, 1.5, you see it has in the single variable polynomial representation, it's got 3 roots at 0. Incidentally, I'm using the stereographic projection from the South Pole. 3 roots at 0. You can see here, here's the polynomial that corresponds with it. We know it's just z to the 3rd. And here's the JM state. Similarly here, you know, we got the polynomial, the roots, and the JM state. And then, you know, you can look at x. You know, this looks kind of sloppy, but that's just because of the numerical, you know, approximation. Each of these is very close to 1, and 1 is the x plus, you know, represents a point in the x plus direction. Similarly, in the y plus direction, each of these is very close to I. All right, so, you know, our eigenstates are working out. You know, that's what we want, right? It's like, that's how we know it's working. And again, you know, like I'm saying, given one of these, you know, a set of these eigenstates, whether in the x direction or the y direction or the z direction or whatever direction you want, I can expand a polynomial in those eigenstates. And therefore I can describe like the constellation or the spin state as a complex linear superposition of those constellations. To make another way of making sure this works is, you know, let's work specifically with the homogeneous representations, 2 variable polynomials. And we should expect that, say, if we take that polynomial and find the roots, right? And then say we rotate each of the roots in the x direction, and then also rotate the whole polynomial in the x direction, the rotated roots should also be roots of the rotated polynomial, right? It's like obvious that that should be the case, but let's check. So we start off with this randomly generated spin 3/2 state. Here's its homogeneous polynomial. And then we find its roots and plug it in to that polynomial, and we get 0 each time. Again, due to the numerical approximation, this doesn't look like 0, but it's some, you know, some shit, you know, to the -16th or whatever.
A red-tailed hawk just flew by my window.
No way.
Yeah, I'm on Riverside Drive. Yeah.
Very cool. We used to have a lot of birds right outside the kitchen here. They were nesting in the some of the like the lights, like light thing. Light
I see a lot of different species. I live near Carl Schurz Park by the East River. I see a lot of species that I haven't seen before. I think it's because of less pollution, because of the shutdowns.
Hear that? Yeah, nature's coming back. So, you know, you can see what I did here, which is like I got the x operator for spin half, and I got the x operator for spin 3/2. I rotate each of the roots, and I rotate the whole state, and then I check that, you know, the rotated roots are also roots of the rotated polynomial, and you see that it's true. Each of these is still very, very close to 0. Just a little check, you know, just making sure we're we're going.
But of course, Matthew, physically it has to be true because the direction of the spin has to do with the direction that you're measuring it in with the magnetic field. So, of course, physically it has to
Well, what I
be
want to
invariant.
what I want to make sure of is that when we have these different representations associated to the different J values, right? And so, I want to make sure that, when it's acting on when it's like the spin half representation is for the roots of the homogeneous polynomial. So I'm going to use the normal Pauli X matrices today, exponentiate them and rotate those guys. And I want to make sure that my spin 3/2 representation, just does exactly that same rotation. In other words, I want to make sure that, rotating the whole polynomial is like rotating the whole sphere, rotating all the roots individually. So I rotate the roots individually, and then I rotate the whole constellation, the whole polynomial, and I want to make sure I get the same result. And that's to check consistency between the different representations. Okay, so here's another little visualization. Let's check this one out. So, okay, so what I've done here is I've just went with the 3/2 state, 3 stars, it's kind of nice. I chose a random spin 3/2 state. I chose a random Hermitian matrix to be its energy function. And I evolve it under that energy function. And at each time step, I convert the JM state into the polynomial and I find the roots. And here they are. You can see them going around on the sphere. This arrow in the middle is the expected value of the spin axis, like the total expected value. In other words,
Matthew, can you just say a little about what the form of the random Hamiltonian is?
Yeah, well, as I say, it's random. So for example, Q-tip has a function that I call, random Hermitian matrix of a certain dimensionality. And it just gives me a random matrix. It's Hermitian, it's equal to its own conjugate transpose. And that's it. I can't say anything. It's just completely random. It just has the right form of an operator, the kind of operator that we need. In order to do the time evolution, I just choose some little time step, dt, in this case, 0.001. And I do the matrix exponential, -I times h times dt. And so this gives me a unitary matrix that just evolves it a wee bit in time. And then I just have a big old loop here. And at each little time step in my simulation, I just multiply the state by that unitary matrix. And then I, find the corresponding polynomial and visualize the roots. But there's more in this. Okay, so what's going on to the right here? I've expanded this state in the Z eigenstates, which is just the normal way that we write the spin vector anyway. By default, we just quantize along the Z direction, just by convention. So these constellations here are, the Z eigenstates. In other words, 3 stars at, at the North Pole, 2 stars at the North Pole, 1 at the South Pole, et cetera, et cetera, et cetera. And each one has a component, and it's a complex number. And so I visualize it with a little arrow. So in other words, what you're seeing here is just the spin vector. In other words, the spin vector by default, we're treating it like it's quantized in the Z direction. And there's, it has 4 components. and we visualize those complex numbers here. So, you know, to the left, you have the roots. To the right, you have, okay, not exactly the coefficients of the polynomial, but the components of the JM vector. Remember, it's a little different because we got to remember that minus sign and some other things. But, you know, the point is that, like, this is an evolving spin state. It has a perfectly definite, quote unquote, constellation. It's just given by those 3 stars. But it is also a linear combination, a complex linear combination of, say, these 4 eigenstates, which correspond each to constellations of their own. You know, just for fun, let's, instead of just choosing a random, you know, Hamiltonian, let's just rotate it around the x direction. Just to see, you know. Actually, let me also just make it go a little faster. A little lazy looking. Okay, so we're just applying the Pauli X operator for spin 3 halves. We see that indeed it just rotates it around the X direction. And, you know, there's some funky stuff happening over there in the components of the vector. But, you know, the meaning is quite transparent. When we look at the stars or the points or the roots, whatever you want to call them, it's an X rotation. The whole constellation is just rotating around the X axis. And this is like what I want to emphasize, like again and again and again. It's like complex linear superpositions sound complicated, but they can be interpreted geometrically. And in this case, they can be interpreted geometrically as just a bunch of points on the sphere. And it has real physical meaning because, you know, we've chosen the operator that supposedly rotates it around the X axis. And indeed, this constellation just rotates around the X axis when we apply that operator.
Matthew,
Yeah.
I lost you. How does this relate to the roots of the polynomial? Are the superposition states the roots? Do they correspond to the roots of the polynomial?
No, it's like you take, here, I'll go back to the equation here. So here's the thing. Though you take the components of the vector, those are going to be the A0, A1, A2, okay? And then we form a polynomial where each of those coefficients weights a power of z. And then there's also a little -1, and then also the square root of the binomial coefficient. So there's just like that little extra bit. But other than that, it's like, morally speaking, you can interpret the components of the JM vector as the coefficients of the polynomial. And then the points are given by the roots of that polynomial. You know, okay, does that make sense?
But how does that relate to the superposition state? So are those the points?
How do you mean? Here, I'll go back to this. I'll go back to this. So, like at each moment in time, this, you know, constellation here is a linear superposition of these 4 eigenstates. In this case, it's the eigenstates in the z direction. So these yellow arrows are just the components of the vector. Or, you know, modulo that little detail about the -1 and the binomial coefficient, they're just the coefficients of the polynomial. And therefore, this state can be seen as a superposition of these 4 eigenstates. But I could have done it in the z, and like in the y direction as well. Like I forget it. I do that so I can do that easily. You Yeah,
Well,
let's,
of course, because physically, every direction is equivalent. It's determined by what direction you're measuring it in.
yeah, exactly. So like, for example, boom, here. Did the exact same thing, but now I've quantized along the x direction. So now you can see this, this spin written out as like a linear combination of x eigenstates, or whatever you like. And it's interesting, it's funny because in this case, it's nice because you see we're rotating around the x direction, and we're also here to the right describing it as a linear combination of x eigenstates. And so you see that, each of these little arrows is basically turning around independently of the other ones. Their lengths aren't changing, just their phases are. How about that? Okay, so that's cool. Another thing that's worth noting, just in terms of like getting like the sort of physical intuition here, right? Like if a state is in an eigenstate of the Hamiltonian, then its constellation will not change. There's just going to be a phase rotation. Perturbing that state a little bit out of the energy eigenstate will cause the stars each to precess around their former location. And there I have a little visualization of that. And actually I showed it to you guys last time. But let us look at it again. All right. So again, I just like the spin 3/2 state because it's got 3 stars. I mean, we could have chosen anything. If you guys want to see some.
It's a delta baryon.
Yeah.
Name a spin 3/2 particle. Victor.
A delta baryon.
Oh, a delta baryon. Okay, I don't know. You got me on that.
Like three up quarks, 3 down quarks.
Okay. I'm going to check that out just to make sure.
It's so easy to visualize these states that
I don't know omega minus though.
I often don't think about like what is their physical significance, like which particles like have these different spin states.
I think it's a purely theoretical idea, but
no, there are actual particles that are 3/2 spin.
No, but three up quarks together or 3 down quarks together. I don't know if that's ever been observed.
Well, that would be a meson. That wouldn't be.
No, a meson is two quarks.
Yeah, but 3 up and 3 down would be 0. Well,
no, but separately. Either 3 up or 3 down would be
I think
delta baryons with spin 3/2.
For a fermion, you need an odd number of quarks.
Let me just mention that 3 up and 3 down has been proposed as a candidate for dark matter by Farrar from NYU. She has proposed systems consisting of bound states of 3 quarks and 3 antiquarks, where the total charge is 0, baryon charge is 0, all the other charges are 0. So the only thing that you are left with that is of any relevance is mass, and you have dark matter. And since I've heard this proposal, I've been rooting for this to be true, because if she is right, then dark matter is family. It's made of quarks and antiquarks.
Yeah, but Moshe, I don't believe in dark matter, but be that as it may, 3 up and 3 down quarks, is that a fermion or a boson? That should be a boson.
It's a boson.
It's a boson.
You guys are just confusing. All of you guys are confusing 3 up and 3 down with 3 up or 3 down.
Oh, it's 3 up or 3 down is a delta baryon. That's a spin 3/2 particle.
That's right.
Tree hop or tree down.
What I said, this confirms what I said. What I said is that you need an odd number of quarks for it to be a fermion. An even number of quarks is a boson.
Yeah.
But I don't believe in dark matter. That's science fiction.
Well, not an even number of quarks, an equal number of quarks and anti-quarks will give you a boson.
Well, yeah, and right, that's correct.
One physicist developed a way of looking at all of the stars in a galaxy separately, and separately, instead of doing the total mass, separately calculating each of the gravitational attractions between the stars. And this, his math was checked by 6 major, mathematician, physicists around the world. And you don't need dark matter to have the kinds of speeds of the stars moving around the edges of the galaxy if you simply do each of the gravitational calculations separately. And there's another 2 physicists that have found that half of the missing dark matter is in the WHIM, the WHIM, the warm, hot intergalactic medium. So dark matter is under siege right now.
Check it out. Philip Mannheim at the University of Connecticut has completely described the rotational curves of the galaxies without dark matter. And I know Moshe is going to jump in and say, but it doesn't explain gravitational lensing. But if there's a halo, some kind of gravitational halo around a real massive object, that could explain gravitational lensing. Dark matter is a fiction. Until we have, empirical evidence, it's science fiction, it's not science.
Well, I don't think anyone uses the term to mean anything specific. It's like, represents more of a mystery than a...
Anyway, so we all apologize for interrupting this fascinating presentation, which none of us understand.
Have you conceived of this from beginning to end? Are these your mathematical analogies? Are these your geometric models? Or are you working on the thinking of others, or synthesizing the thinking of 2 or 3 physicists? What are you doing here?
Right. So, as I say, it was like Majorana in the 31st, I would say, promoted this representation of the spin as polynomial. Today, it's standard. Like if you go on like the Wikipedia article for representations of SU2, like they will talk about the polynomial representation of it. So it's pretty standard stuff. It's just not always emphasized, I suppose. In terms of, other papers, later on, I rely on the work of a guy, LaBeouf. There's a great paper called like the phase space picture of quantum mechanics or something like that. There's a guy, I think his name's Patrick Bruno, who has done some more work recently and relating the evolution of these quantum systems to a classical system that lives on the surface of the sphere. So none of this mathematics or this physics is original to me. Just the simulations are.
So it's a palimpsest.
It's palimpsest.
Going back to the very beginning of the talk, it's a palimpsest.
Yeah, I just found that looking over the references, there wasn't really one place where someone talked about the whole thing and all of its interconnections in great detail. So that's sort of what I was doing. And I like it because it just, spin systems are pretty simple. You know what I mean? This is not that complicated. As far as quantum systems goes, this is just a finite dimensional vector space. It's represented with polynomials. But in some ways, all of quantum mechanics is contained in here. You know, we got a Hilbert space to play with. And so, you know, without getting into a lot of mathematical technicalities, you know, we can discuss some of the profound mysteries of quantum mechanics, you know, using what is arguably the simplest possible quantum system as a toy, you know, in order to talk about it. So, you know, in terms of this simulation here, what I wanted to show you is that. So again, I'm controlling this with my keyboard. It listens to the keyboard, like it does stuff. Okay. So, for example, I can, you know, pause it, and if I hold down like the A key, it'll do like an X rotation. You know, I can go in reverse. You know, I can do a Y rotation and so forth. I can clear these trails. At the top there with that yellow arrow, that's the overall phase of the wave function. Just so you can see it. Because remember, the state itself is defined by the constellation and also the overall complex number that you can multiply the polynomial by. So that's just there for completeness. In terms of what I was saying about energy eigenstates, so again, we've chosen a random Hamiltonian, and what I will do is I will measure the energy. Okay, so now I have, like I'd chosen like a random Hermitian matrix to be the energy. It was evolving under that Hamiltonian, and in fact, it still is. Except what I've done is I looked at the probabilities and I collapsed it with a certain probability into one of those energy eigenstates. And we can see that in an energy eigenstate, you know, because it's an energy eigenstate, like, you know, the state remains the same, like to wit, the constellation remains the same. And all there is just a little phase evolution. But because I programmed it in that I can also do these XYZ rotations, let me just rotate it like a wee bit, you know, around the X direction. And so what I've done is I've perturbed it ever so slightly out of the energy eigenstate. And you can see that the effect of this is to make the stars sort of precess around their former locations. Let me do it again. They're pretty much still kind of going around where they were before. The more I perturb it, the more wild it gets. And you can see at a certain point, the stars start permuting. Like instead of just going around their former locations, they start swapping places. You see here, it's about to happen. Oh, look what they're gonna do it. We're gonna do it. Is the brown and the dark green gonna swap? They already did it once. Oh, there they go. See ya. Nice. That's kind of interesting. You know, if we keep perturbing it, you know, eventually it'll become ambiguous. You know, what were those original points that it was rotating around? And that's as much to say we're now in, you know, we're quite far from that original energy eigenstate. We're in some, you know, just general superposition of energy eigenstates. Furthermore, I want to note, like, you know, look at the dynamics of this thing, right? It's like these stars or points or whatever we want to call them moving around. But look, like whenever they get real close to each other, they kind of like deflect, okay? And like this should remind you of kind of like charged particles, you know? Like they're like, it's as if they're experiencing force that like, you know, gets stronger like the closer they are together. So like when they get closer, like, bam! And we're gonna make this like analogy between these points and quote unquote little charged particles more explicit in a moment.
Matthew, I lost you. Did you say this is still the random matrix, still the Hamiltonian derived from the random matrix, or have you made this more specific?
So again, it's just a random Hamiltonian. In fact, I can press the O key and I can just pick another. I'd like now I'm just changing the energy function. Again, yeah, it's just randomly chosen. But once I've chosen it, I can press this key, which collapses the state at random with the right probability into one of those energy eigenstates. So we've chosen a random energy function, and we've just tried to visualize the constellation of one of those energy eigenstates. And that allows us to see, when we perturb it out of an energy eigenstate, the motion of the stars is quite simple to describe.
So to repeat what you just said, this is a random Hamiltonian, and then you pick one of its eigenstates. So it isn't, so these eigenstates really don't tell us, I don't know how to put this. They don't tell us anything about a particular system because you've randomized over all systems. You're just saying, after I've made a random pick of whatever Hamiltonian could possibly be, I then find an eigenstate of that and just look at that in its own basis.
Yeah, so like basically, we're not trying to model any particular physical situation. We're just, I just randomly sample from the space of, finite dimensional Hamiltonians. And, because the spins live in a finite dimensional vector space, the energy function just amounts to choosing some random, in this case, 4x4 Hermitian matrix.
Yeah, I guess what I'm confused about, Matthew, is I guess, as you keep saying this, is exactly what random means here. Because you've somehow picked a basis for the matrix and then randomized each element of the basis of the matrix. But if you would have picked a different basis and randomized, that would be like picking a different distribution to randomize from.
So, right. So if I understand your question correctly, it's like what I'm doing is the spin itself remains quantized along the z direction. Okay. So I'm still just working in the z basis, but I just choose a random energy function. And then in the z basis, it has its eigenstates or whatever. And then I, collapse this guy into one of them.
Yeah, I guess that's not exactly what I meant, because you're saying the system has a basis, but I'm pushing you about whether the Hamiltonian has a preferred basis in which you're randomizing.
Well, so are you saying like we could instead have expanded the spin vector in the particular basis given by this Hamiltonian, and then looked at, like, say, the constellation in terms of that? Like, then we would have a spin vector in a different basis. We could find, like, the polynomial and then find the roots, and it would be a different constellation.
I think that's right. I think what I'm pressing on is what random means in the particular
So you can,
for the particular matrix.
in this case, it's sort of like
this is not it's not a univocal kind of interpretation to randomize a matrix. You have to pick a basis for the matrix and then
right. So this is like
randomize the elements.
It's like I don't know exactly the algorithm that Qt uses to generate its random Hermitian matrices. But it's like sampling, from this like random matrix ensemble. And yeah, like that matters. I mean, to the extent that like a lot of relevant Hamiltonians, like you'll never pick them. Like, you know what I mean? They'll be like measure zero. Like similarly, like when I pick, like say, when I generate a random spin state, like a typical state that you'll get, like for example, like will almost with measure zero will be like, it'll never be like, say like a Z eigenstate where like all the stars are in the same location. Like you're never gonna get that state by just choosing like randomly. So yeah, so like, yeah, I mean, so you're not, so when you randomly sample these things, you're getting kind of like typical in some sense states and matrices. And there are going to be some like very relevant Hamiltonians, very relevant states, which like the chances are like you're never going to sample like when you do it this way. But you know, the point of this is more to explore, is to use this as like a way of exploring this particular like representation of spin, rather than to worry about like what is the physical significance of like a particular Hamiltonian. And you know, a Hamiltonian you might care about like might be one that you're like never gonna get by doing this random sampling. Okay, so here's a cool thing. So this, in what follows, and again, I'll upload more papers and stuff, like give more like complete bibliographic references. The following discussion follows this paper again by LaBeouf, I think from the 70s. And he talks about how to find the time evolution of the individual points on the sphere. So as I say, what I've been doing is just taking a JM state, you know, and then I got some Hamiltonian, I just evolve the state, and then I, at each moment, convert that state into a polynomial, find its roots, and visualize it. But you could be like, well, you know, I got, like, why can't I somehow find like a mathematical expression for the time evolution of the roots individually, rather than go through the trouble of like breaking it down to polynomial and finding the roots like at each little discrete time step of my simulation. And so you can. So what this little next section is about is, suppose we have some roots, rho I, and we want to calculate the time derivative of each of those roots. And so here's sort of an argument for basically like how you can do this. So, you know, for sake of argument, let's choose a polynomial with two roots, alpha and beta. And we'll consider those roots to be functions of time. So now we have like f of zt equals z minus alpha t times z minus beta t. Since the roots determine the polynomial up to, you know, a complex factor, that's like a perfectly good way of parameterizing the time evolution of this polynomial. If you, you know, multiply it out, you get this. And then, you know, I'm not going to justify every step here. I'm just going to show you that it works. So let's take the partial derivative of this with respect to time. So you fiddle around a bit and you get, okay, the change in time with respect to alpha times beta t minus c plus the change in time of beta times alpha t minus c, where we've used the chain rule. So we have our little polynomial f of zt, and we take its partial derivative with respect to time. But we could also take the partial derivative with respect to z. When we do that, we just get 2z minus alpha t minus beta t. Now, here's the cool thing. Consider this expression, where we take the time, the partial derivative with respect to time over the partial derivative with respect to z. And we get this expression here. Change in time of alpha times z minus beta t plus change in time of beta times z minus alpha t over 2z minus alpha t minus beta t. I've just substituted, you know, substituted in there. And there's a little minus sign. Now here's the cool part. What happens if we substitute in alpha t for z? So in this expression, we got these z's. So like, let's plug in alpha t for those z's. So blah, 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 blah. You know, alpha t minus alpha t is 0. 2 alpha t minus alpha t is just alpha t. And then we get, you know, derivative of alpha with respect to time times alpha t minus beta t over alpha t minus beta t, but that cancels out. And we just get the change in alpha with respect to time. In other words, the time derivative of a root, rho, is given by minus the partial derivative of the polynomial with respect to time over the partial derivative of the polynomial with respect to z, evaluated at z equals the root at a given time. So that's kind of cool. Like that works in general. Like, you know, if you have some function, like some polynomial that's like time dependent, you know, you can find the time evolution of the roots using this little trick. In the quantum case, you know, we'll be considering like the Schrödinger equation, where we have like the partial derivative with respect to time of f of zt equals minus I times h, where h is a differential operator. That's Hermitian, corresponding to the energy, and that's multiplied by our f of zt. So, you know, but look at that. Like, what is that's just saying? We now have this expression for the partial, the time derivative of f of zt. It's just negative I h f of zt. So plugging that into our former equation, you see we just replace partial derivative with respect to time with I h f of zt, and we get this. Okay? And now here's an interesting point, which is that, you know, since h is a differential operator, we can express it as like a sum of some stuff times, you know, the first derivative times some stuff plus some stuff times the second derivative, etc. Right? So we can write like the differential operator as a sum in the nth derivatives with respect to z.
Are you still going to be able to sort out all this stuff at the end, or is it going to end up in the quantum landfill?
Well, how do you mean? So here's the punchline. So
Wait, Matthew, I didn't get it. Is h assumed not to be a function of t, an explicit function of t?
yeah, in this case, we're assuming h to be, yeah, like time independent.
How's that possible?
Happens. So, you know, basically the point is that in this expression for the time derivative of the root, we have this h, this differential operator. But we want to kind of look under the hood of that. So we're going to write it as a sum of some cn's, which are functions of z, each time an nth derivative with respect to z. So plugging that in, we get the time derivative of the root with respect to time is I times sum over n of these functions of z, one for each n, times the nth derivative with respect to z of f of zt over the first derivative with respect to z of f of zt, evaluated at z equals, you know, rho t, where rho is the root. So what's cool there is now we don't have any time derivatives anymore. We just have derivatives with respect to z. And here's the punchline. This is just generally true. Like if you take the limit as z goes to rho t of the nth derivative with respect to z over the first derivative with respect to z, that has a very simple algebraic expression. I've worked it out in a couple simple cases here. So suppose we have this polynomial here with 4 roots. Then when n equals 1, this is just 1. When n equals 2, we get this, which is like a sum of where, a sum of the, wait, is this how I want to do it? I'm sorry, I made a slight mistake, which is that I want, instead of alpha there, that should be rho. Sorry. My bad, that should be rho. So it should be like rho minus beta, rho minus gamma, rho minus delta. And then in the next one, rho minus beta times rho minus gamma. Okay, so everywhere we're here, you see alpha, just mentally replace that with rho. My apologies. Okay. So what this looks like is an interaction where so like in the case of, you have the second derivative here, it's saying that there's like an interaction between the root rho and each of the other roots taken separately. So this is like a two-body interaction between a given root and like the other roots. For the third derivative, we have a two-body interaction where rho interacts with beta and gamma, rho interacts with beta and delta, rho interacts with gamma and delta. In other words, the root interacts with the other roots taken two at a time. And then here we have an interaction term where the root interacts with the roots, the other guys taken three at a time.
Matthew, do you have an intuition for what's the physical meaning of roots interacting?
Right, so like I was saying, they're like little charged particles. Each of the roots is feeling a force that is generated by the other roots. And it's not like exactly like electromagnetism, like in the sense that it's a force which has, so like for example, here I've got it out for, I've written it out for, suppose there's 4 roots. The time evolution can be written in terms of these arbitrary functions of z, c1, c2, c3, and they are waiting. So we have a little piece of this evolution that only depends on where that root is now. Okay, so it's kind of like a zero-body interaction.
Question.
And then we have a term here where that root's feeling a force that depends on its relative location to the other stars. Okay, and then we have over here a term where the interaction depends on the location of pairs of other stars. So,
I have a question. Correct me if I'm,
interaction and so on.
can you hear me?
Yeah.
Correct me if I'm wrong, but this seems to imply that we can solve the roots of an n polynomial equation when in fact you cannot. We've been told you can't solve where n is greater than, you can't solve for greater than a 5th order equation. Also, I have a second part. The 3-body problem has not been solved. This implies that you could solve it.
What do you mean, right? Like in the case of like the law theory that you're talking about, it's like to solve means you have a like finite algebraic expression where you plug in the coefficients and you get out the roots. So, you know, when that's not possible, you know, it doesn't mean there aren't roots. It just means that it would require an infinite amount of algebra.
Oh yeah, it implies that you can't solve an enclosed form. Of course, every equation has roots, but they can't be solved in closed form. But how does this relate to the 3-body problem, which can't be solved? This implies that the 3-body problem can be solved, I believe.
You know, I mean, you'd have, I don't know what you mean. It's like,
well, the sun Earth moon system cannot be solved exactly.
Like if you wanted to calculate like the long-term dynamics of, you know, a 3-body interaction, then it would be in principle chaotic, right? Like,
no, not necessarily. The sun Earth moon system, it's not chaotic.
But that's a stable 3-body system, and with, you know, it's far more difficult to solve one which is, you know, 3 bodies that are approaching one another, and then you get all of these, you know, interactions, rotations. You get bodies
Victor,
being
in
propelled.
general, the 3-body problem, the 3-body gravitational problem cannot be solved in closed form.
I agree.
But this seems to imply that you can solve it. Or am I mistaken? What am I not seeing here?
Well, all I've done is I've like taken the root, or like the polynomial or whatever, and kind of rewritten it. You know what I mean? Like up here, I just, you know, fiddled around and then derived this like expression for the time derivative of a root, you know, where it's like time derivative over the derivative with respect to z.
Well, this is practically.
I was able to like substitute some things in there and like expand that as like a sum over these like n-body terms. So it's just like giving you a sense of like, in a way, the physical intuition behind it. Like you can think about.
Right. I think that the problem in this discussion between Matthew and Michael is that Matthew is using a metaphor in talking about three bodies. It's that what he means by three bodies is three roots of this polynomial equation, not three particles moving in space under some force law.
Okay, agreed, Andre. But
But I mean,
how does this relate to an nth order polynomial? We were always told that you can't solve a polynomial in closed form for greater than fifth order.
well, look, I mean, again, one way of saying it is like this, like, when I started up here, like I already assumed this factorization, right? Z minus alpha t and Z minus beta t. And then I was interested in the time derivatives of those guys. So, you know, I don't know what to say. It's like, you know, when I'm doing my, the Python code, like, again, you know, I'm approximating the roots or whatever. You know, initially here, we're like treating it like the roots are already solved out for, and we're looking for the time derivative. I don't know, maybe that might answer the question. But I want to emphasize, you know, it's like, again, like this is a, you know, it's sort of a metaphor, but it's also like not. Like it's just, these are like particles on a sphere. So they're not just like in just normal old 3D space. And they're feeling, say, you know, if C1 and C2 and C4 here were all 0, and you just had some thing here, then this would be, you know, like a three-body problem. It's like, it's not a metaphor.
And since it's not a metaphor, is there some relationship between the process of approximation and probabilistics?
Not that I know of. Not.
Okay.
Here's a, you know, just a little, we talked about this a little bit last time. It was just a screenshot from Majorana's original paper where he's just considering a spin half particle in a magnetic field where the field's in the hx, hy, hz direction. And he finds this expression for the time derivative of the single root, where that's just this zeta here. And you can see it has this relatively simple form.
Is tang hyperbolic tangent? Probably Italian for hyperbolic.
Oh,
tangent. Yeah.
I think it's just the normal tangent, but I'm not sure actually.
Oh, maybe it is. Yeah, and maybe
It is the normal tangent.
The normal tangent.
Yeah.
Oh, okay.
Can I just point out again that this is very far from what's normally thought of as a three-body problem in three-dimensional space with a 1/r² force law. Here you have this.
Yeah, we're on a sphere.
You're restricted to a sphere, and the force law is what follows from this Hamiltonian on that sphere.
Yeah, no, I understand that, Andre, but I was just curious if this works for, let's say, a 10th order polynomial, 10th degree polynomial.
Yeah, like it you know, the degree doesn't matter. You just get these like higher order n-body interactions in general, right? So I'm gonna skip forward a bit. So like just to give some more intuition about like the whole polynomial thing. Let's talk about spin coherent states. And this is a very beautiful thing. You guys are gonna like this. This is gonna like make a lot of sense, all right? Like really feel like why this polynomial thing works in a fun way. So the spin coherent states, later on, by the way, we'll talk about the coherent states of the harmonic oscillator, but these are just spin coherent states. And the idea is that they're states where all the points are in the same location. So if you have spin J state, there's gonna be 2 J stars at some point on the sphere. So that's a spin coherent state.
Again, Matthew, as you keep using this metaphor, when you say same location, you mean that the vectors specifying the basis of the spin state are at the same point on this two-sphere. Has nothing to do with location in space.
The roots are in the same place on the sphere. And we'll see exactly how this sphere relates to like the actual directions in 3D, like when you go to measure a spin. So actually, I'm gonna skip this part. Okay, so here, all right, so this is the cool part, right?
So it's a metaphor about an allegory about a metaphor?
This is all very literal.
Hey, Victor, how's that bird doing?
I'm dogging him.
So here's the thing. We can use the spin coherent states to define a kind of wave function on S2 corresponding to our spin state. In other words, we could imagine we have some spin state psi, and we could imagine taking the inner product of that spin state with the spin coherent state where there's, 2J points at the point XYZ. So I'm denoting, XYZ here, the spin coherent state with 2J stars at XYZ. That's a point on the sphere. And we can form this inner product. And so you can see, I just have like this, this state psi. I can basically turn it into a function of XYZ using this inner product. Now this wave function is going to be 0 at the points directly opposite to the Majorana stars.
Wait, Matthew, you just go so fast for me. Psi is a state giving the amplitude of a measurement of the spin direction.
Psi is just a spin state in the JM representation.
That's right. So it says if the particle is at position XYZ, is that in space XYZ? That's physical space. And then saying what's the amplitude of its spin in the Z direction when the particle's at that position in physical space.
No.
So XYZ are not physical space.
Well, they are, but what I mean is it's not the probability in the Z direction. You see, psi XYZ is the probability amplitude for all the stars to be at the point XYZ, right? Like XYZ is a spin coherent state. It's like the state where all the points are at this one part, right?
That's right. So XYZ there is in your spin space and not in physical space, not location in physical space, but location in not location in geometric space, whatever you want to call the space we live in. It's a point in the spin in the space that describes the spin vectors.
And that space is also the 3D space that we live in. In other words, this is actually how we can relate the spin space to the familiar 3 dimensions that we live in. In other words, if we send the spin through a Stern-Gerlach, then these points, can I say this right here?
It's just I'm trying to figure out, Matthew, I'm just trying to figure out what psi of XYZ means to you.
Andre, it's like, X, Y, and Z are arbitrary. You can rotate them. They're rotationally invariant.
I get that. That's not my point.
But it's like the Schrodinger equation. It's like the Schrodinger equation. Where X, Y, and Z are not.
I get that, Michael. It's a question of what is X tell you something? Is XYZ a point on that sphere, or
Yeah.
is XYZ a point in the position space of where the particle is?
No, it's not. Yeah, it's
I
nothing to do
think
with
it's the
where
sphere.
it is. It's just on the sphere. Yeah, yeah.
Right.
Okay, so, psi xyz is like a probability amplitude for all these points to be at xyz. But it's like, suppose we have one of these Majorana stars like in the opposite direction. Well, then that amplitude has to be 0, because since there's a point in the opposite direction, there's no way that all the points can be in the opposite direction. So the zeros of this inner product are precisely the opposite of the zeros of the Majorana polynomial. They're just antipodal to each other. And so this gives us an operational meaning for the points on the sphere, and relates the sphere to the actual, three-dimensional space that we live in. They represent the directions along which there is a 0% chance that the spin will be entirely in the opposite direction. That's the meaning of the Majorana stars. They're the directions along which there's a 0% chance that the spin's entirely in the opposite direction.
What's the probability that Majorana is still alive? What happened to him?
The man disappeared.
He disappeared. Nobody knows. Well, there is a theory. There's a theory that the fascist government in Italy, he apparently was politically active, and he was against the fascist government. So they may have disappeared him.
Could be. All right, so check this out. Here I've done it. So what I've done is like I've chosen kind of gridded out the sphere, and I formed the spin coherent state at each of the points on the sphere, and I took the inner product with a particular state that is evolving in time. And at each point on the sphere, I've put a little arrow, and that arrow is the amplitude. And I visualized the zeros of that function. So these are, okay, so I just want to emphasize, the Majorana stars are precisely antipodal to these. So these are like those 0 probability points, literally. And, you can think about this as indeed like a wave function on the sphere. And it is completely defined by the places where it's 0, in the same sense that a polynomial is defined by its roots. So, if we wanted to just like sort of be like more explicit with regard to what we were doing before, I will, all right, so now you see both the, these are the Majorana stars now. In other words, it's just the antipodal points from what we looked at before. And so the idea is that the wave function on the sphere is always 0 opposite to these points. So if I like look at the opposite point of the sphere, like directly opposite to each of these points, there's gonna be, you see, 0% chance that the spin is entirely in that direction. In other words, this amplitude is 0. So we can relate these points on the sphere to experiment. Like, this is not an abstract, this is like not a metaphor, like this is like literally the 3 dimensions of space that we live in, and this stuff has an operational meaning in terms of probabilities that you can obtain when you measure this particle in different directions. And we can relate it as well to a more familiar kind of wave function on the sphere. Now, there's some caveats with regard to that in the following sense, which is that the spin coherent states, while they form a basis for the spin states, they form an over-complete basis. In other words, they are linearly independent, but not orthogonal. And so you can't interpret these little arrows as being literally probability amplitudes. Now, in the sense that you can look at where the probability is 0, like you can really interpret that as 0 probability, like that doesn't affect that argument. But the idea is, the interesting fact is that when you take the limit where the J value goes like to infinity, in other words, we take like the kind of classical limit, then the spin coherent states do become orthogonal. And in that limit, we can interpret this wave function on the sphere as a perfectly good wave function. And you know, to get more intuition about why this works, like let's follow some stuff out a little bit here. So I want to make more precise this claim that we have this H. I call it H because it's often called the Husimi distribution on the sphere. That this like little inner product Z, where okay, before I was like representing the spin coherent state, I just wrote it as like a little XYZ vector. Okay, but now I'm just writing it as Z. But again, it doesn't matter, right? Like this Z could be a complex number of infinity. That's also an XYZ point. I'm just playing around with how you can write it. So I want to make precise this claim that this inner product of psi with spin coherent state at Z is intimately related to our Majorana polynomial M of Z in the sense that they are just antipodal to each other. It's just the constellations, the stars all just sent to the opposite point on the sphere. So we can prove it, and this is kind of fun. So suppose we have a spin 1 vector, ABC, all right? We can form also a spin 1 coherent state where we have Z minus alpha, where alpha is just, you know, a point on the sphere, and we're not gonna specify it because we want to consider all the spin coherent states. And we want it to have degree 2 because we want it to be a spin 1 state, so it has 2 stars. So we get this polynomial Z squared minus 2 alpha Z plus alpha squared. And then we can convert this into a ket using the little, the trick, right? So, you know, we just had to flip the sign there. We had to put, you know, divide this out by the square root. And we get this JM vector. And now the sleight of hand is, oh, okay, I'm gonna just rename alpha to be Z. And then I get this. We could normalize this. We really should normalize it. The length of this vector should be 1. So, you know, we and you find out that the normalization factor is 1 over 1 plus the absolute value squared of Z. All right. So now let's form the inner product, psi on Z. Now, before we wanted Z on psi, but you know, it's actually easier to see if we just flip it around. So we have some, so remember psi is just some spin 1 state, ABC. We conjugate it, and we take the inner product with this spin coherent state where there's 2 stars at Z. And we get this polynomial. And you see already, like, it looks kind of like the right polynomial, except that what? Well, A, B, and C are conjugate to each other, and they're all flipped around. So the order has been switched. It's not ABC, it's CBA. Now here's some interesting facts that are not like entirely obvious about the relationship between the complex number representation of a point on a sphere and the, you know, the normal representation. So for example, if we take a complex number and divide it by its norm squared, that flips the stereographic projection pole from north to south. If we take a complex number, divide it by its norm squared, and say multiply it by -1, then that sends the point, the XYZ point, to the opposite point on the sphere. And it turns out that that generalizes to the general, degree n polynomials. In other words, if we take a complex vector and flip its components left and right and complex conjugate the elements, we swap the projection poles. If we take a complex vector, flip its components left and right, complex conjugate the elements, and multiply the nth component by -1 to the n, in other words, multiply every other component by -1, then it sends each of the roots to the antipodal point on the sphere. There's a little code that, that does that. So then here's the punchline. We have this polynomial, and we said that this, we could call it the spin coherent amplitude, should have zeros that are opposite to the Majorana stars. So let's take h of z and invert its roots, send its roots to the antipodal points. How do we do that? Well, just like I was saying, we flip it left, right, complex conjugate all the elements, and add in the -1 in every other term. And then we get h of z is just this little normalization factor times az squared minus 2 over 2 square root of 2bz plus c. Now this normalization doesn't affect the roots in any way. So then we can take this polynomial and convert it into a spin vector. And we just use the Majorana polynomial in reverse. So that just boils down to multiplying the middle term by -1 over square root of 2. And so we end up exactly where we started with the spin vector ABC. So you follow that, it becomes undeniable that this really works. Okay. Furthermore, we can talk about like the inner product in terms of the polynomial. This should say spin half. So, suppose we have two spin half states. I just chosen them, to be kind of like not that complicated. 1 over square root of 2, 1 over square root of 2i, and then this guy is 1 over square root of 5, 2 over square root of 5. Now we know how to take the inner product, right? It's easy. We just take, the conjugate of f, then, pairwise multiply it by the elements of G. And we get, 1 over square root of 10 minus square root of 2 over square root of 5 times I, which is just 1 over square root of 10 times 1 minus 2i. Okay? So, that's easy enough to do. The question is, can we get that same answer in terms of the polynomials? In other words, when we're working with the polynomials, we want to kind of work with, integrals instead of finite sums. All right, so can we do that? And you can see here where this normalization factor is going to come into play. So we have f and g are two spin half states. And we can represent them by these polynomials using the little Majorana formula, where we just put in the normalization factor there. And that normalization factor is going to scale 1 over 1 plus absolute value of z squared to the j. Now, to express the inner product in terms of the polynomials themselves, ultimately what we're going to do is we're going to integrate over the complex plane. So, we're going to be working explicitly in this infinite dimensional space of polynomials. And there, the inner product becomes an integral. We take, the integral of the complex plane of the conjugate of f times g. And actually, there's a little bit of a technicality here, which has to do with some funky complex number business, and I don't want to go into the whole story here. But it turns out that, in general, when you take an inner product between functions, you have to specify a weight function or a measure. And it turns out in this case, the correct weight function to use is 1 over 1 plus absolute value of z squared to the 2j plus 1. And there's an interesting story about why that is. but let's leave it to the side right now. So in this case, j is 1/2. So, you know, here you have it, like 1 over 1 plus absolute value of z squared, that's our weight function, times here we have f conjugate, and here we have g conjugate, okay? And, you know, sussing this out here, you know, kind of like distribute out this little conjugate operation, take out a factor of 1 over square root of 10, we get this guy. And then, you know, to actually take this integral, we gotta, you know, express z as r, some r to the ei theta. So we substitute that in, and as is usual in these cases, in order to get the right like normalization, it turns out you have to multiply it by 2j plus 1 over, in this case, pi squared. It's a classic kind of thing to do. And here's the thing. You type this into Wolfram alpha, you have r squared plus e to the I theta minus 2 e to the negative I theta times r minus 2I over 1 plus r squared. All that squared, integrated over the complex plane. So we integrate where theta goes from 0 to 2 pi, a full rotation around the complex plane. And for r, where r is the radius, from 0 to infinity. And we find that that gives us exactly 1 over square root of 10 times 1 minus 2i, which is exactly what we got over here. So, you know, obviously, like doing it this way, where we just, you know, we're working with these finite dimensional vector spaces, we can just, you know, find the inner product in this normal way with a finite sum. In this case, is like obviously going to be way easier. But in principle, you know, we can work directly with the polynomials and define the inner product in terms of an integral. That is yet another way of showing the consistency of this scheme. And crucially, you know, it's useful to work in this representation because when you're working with the polynomials in themselves, you know, you can imagine, you know, having, say, an infinite number of roots, right? There could be an infinite number of terms to this polynomial, which is like not gonna fly if you're just working with, you know, a standard JM representation or whatever. But here, you know, we are taking like an integral of polynomials over the complex plane. And so it becomes possible to think about basically like the classical limit of a spin, which is in effect a spin coherent state where there's like an infinite number of stars at a given point on the sphere. And as I say, when we take that classical limit and we're considering the spin coherent states where there's like an infinite number of stars at each point on the sphere, then this little amplitude here is like each of those spin coherent states are in fact not just linearly independent, but also orthogonal. And so this gives us like an earnest wave function on the sphere. And, you know, we can think about that like in terms of being like an infinite number of stars on the sphere, as I say. And like what that would mean, like when you think about, you know, if you know anything about coherent states in like other, like say like harmonic oscillator coherent states, which we'll talk about later, they're defined as being eigenstates of the annihilation operator. In other words, there's an infinite number of stars, and so removing a star shouldn't make a difference. So, you know, what that would mean is that, you know, like our polynomial or like whatever is going to be an exponential function. Because taking the derivative of the exponential function basically leaves it the same. And so, you know, you can think about like these spin coherent states as being kind of like finite approximations to the exponential function. You know, what's interesting about them is that, you know, if you have, say, a spin coherent state where all the stars are at x plus, so that would be z minus 1 to the 5th, say there's like 5 stars there. If you take the derivative of it, it's just 5 times z minus 1 to the 4th. In other words, taking the derivative doesn't change the locations of the stars, it just pops one off. And in the case where, you know, we're dealing with like a exponential function literally, then taking the derivative would have like no effect. One consequence of all this stuff is that, you know, instead of working with like our finite dimensional matrices, we can work directly with like differential operators in the traditional sense on the polynomials. So for example, we can represent here's sort of a way of writing it. We can represent Pauli Z as a differential operator Z times derivative with respect to Z minus J, where J is the J value. Similarly, in these representations of SU2, there's the like ladder operators, which, you know, sigma plus and sigma minus will like pop you up from one M value to another. So, you know, if you start the lowest weight state, then, you know, acting with sigma plus is going to pop you up to the next M value, pop you up. And our friend sigma minus is going to pop you down. And these two have representations as differential operators. We can represent sigma plus as 2jz minus z squared ddz. And most beautiful of all, right? Like and this is actually implicit in what I said up here, the sigma minus operator, the lowering operator, is just take the derivative with respect to z. So for example, you know, it turns out that you can write Pauli X as, you know, a linear combination 1/2 sigma plus plus sigma minus, and sigma Y similarly as a linear combination of these sigma plus and sigma Y. So then we can, from that, get expressions for Pauli X and Pauli Y, jz plus 1/2 1 minus z squared dz, and jz minus 1/2 1 plus z squared ddz. Then we can, you know, recast the Schrodinger equation, you know, totally like in terms of these complex polynomials. Like normally, like when you're working with the Schrodinger equation and you're working with like wave functions, you know, the wave function is like a function from, say, like in the one-dimensional case, the real line to the complex numbers, where the complex numbers are the amplitudes. Here, you know, we're working with like just general complex polynomials that can take complex numbers as inputs and give complex numbers out. And we can recast the Schrodinger equation as just like this. So for example, if we wanted to do a Z rotation, we would just plug in the expression for the little differential operator for Z, and it would amount to solving this differential equation that d psi dt equals negative iz times z psi dz plus ij, where j, you know, is the spin j part, whatever the j value is, times psi of z. I implied earlier that, you know, when we're working with like a differential operator, we can expand it as a sum in like the nth derivatives. And, you know, like another way of, and, you know, I want to bring that up again here. But first, like a little review. I'm going to say a couple things I already said, but in a slightly different way. So, you know, consider this. Like, what if I took e to the conjugate of z times sigma plus? I could expand that as an infinite series. in what susses out to being powers of Z conjugate and powers of sigma plus, where this just comes from, the infinite series for the exponential function, but where we're, plugging in matrices instead of just numbers. Now, if you look at what each term of this does, like suppose this guy e to the Z conjugate sigma plus was acting on the lowest weight state. So the negative J state. Each one of these terms raises the M value of that state. Like the first term just leaves it there. The second term raises the M value of 1 and multiplies it by Z conjugate. The next term raises the M value by 2 and then multiplies it by Z conjugate, and so forth. And then you add it all up. So what does that give you? It just gives you like the Majorana representation in disguise yet again. In other words, we can rewrite e to the Z conjugate sigma plus acting on the lowest weight state as just sum from m equals 0 to j. We have our little square root of the binomial coefficient. We have these basis vectors, and we have our variable z. And this means take the conjugate there. I didn't do that before, but we'll see like why that is just like makes it nice, because if we then define psi of z to be the inner product of Z conjugate and psi, where again, Z conjugate is the spin coherent state, et cetera, et cetera, et cetera. And we can rewrite that as this, which is just literally the Majorana polynomial from before. So, you see there's like this intimate relationship between the polynomial representation, the spin coherent states, and, we can write all the things that we normally do with like the Pauli matrices and stuff as differential operators that act on the polynomial representation. We can similarly, not just expand a state in terms of the spin coherent states, in other words, in the Majorana representation, but we can also expand like operators. And so, using some tricks or like whatever, like the Baker-Camper-Hausdorff formula and so forth, we can, so, if you look at what's happening here, we can write this bra Z conjugate as e to the Z sigma minus acting on negative J, okay? Where this is just the adjoint of e to the Z conjugate sigma plus. In other words, e to the Z conjugate sigma plus gives us the, the spin coherent state or whatever, from the lowest weight state, negative J. If instead, where that's a ket, but if instead we work with the bra, we have to take the adjoint of the operator. And so, taking the adjoint of that, the adjoint of sigma plus is sigma minus, the adjoint of, Z conjugate is just Z. So, E to the Z sigma minus acting on negative J is just that spin coherent state at Z conjugate. So, that explains that part. And then here we just expand this out where we just split it into 2, right? Because e to the negative Z sigma minus times e to the Z sigma minus is just 1, right? So that's really just trivial, except to say that then once we have things in this form, we can, use the Baker-Camper-Hausdorff formula to write out that as a as a sum where, you know, if you're familiar with this kind of thing, it's like basically like a Taylor expansion, but where the derivatives are replaced by like the repeated commutators with the operator and sigma minus. And remember, what is sigma minus? Sigma minus in the polynomial representation is just take the derivative, right? So, you know, this amounts to saying, you know, like I was alluding to before, you know, we can expand a differential operator in terms of the nth derivatives, and that's just what this is doing here. So that's kind of the bulk of the kind of the math in terms of like, you know, spin coherent states, why does the polynomial stuff work? And so like if there's any questions about that, like now would be a good time to ask them.
Multiverses.
Matthew, since you're not getting any questions, let me give you the question that I think is below the fact that you're not getting any questions. And that is, we would all, I think, love to hear an elevator speech, a 2-minute representation to someone who never heard anything you said, to a standard physicist, what you just showed us in the last 4 weeks.
Okay. The last 4 weeks. Okay, so right, all right, yeah, we can do that. So in order to discuss the question, which has dogged philosophers for thousands of years, about the degree to which things can be reduced down to like basic elements, you know, reductionism, what are the basic atoms into which we can divide the world, on the one hand, and the view that in some sense there are phenomena which are holistic, or to sort of poke at that question, I started from the simplest place possible, which was like a single pebble. Because, you know, whatever else you can say about like the world, whether it's made of atoms or not, a valid question you can ask is like, what do human beings mean by an atom? And for example, we can use them to signify things. If we agree on the presence or absence of the pebble, whether one or the other will be significant, we can use a pebble to communicate, you know, one bit of information. And then I sort of engaged in a sort of dialectical unfolding of this idea of atom or pebble or number, where we imagine we can have multiple pebbles. And so we can now have like a pile of pebbles. And this gives us the idea of a counting number. Then we keep iterating and we get the idea of the integers, where now we can have both, you know, positive numbers and negative numbers. We then continue this process of iteration to get the rational numbers, where, you know, now, for example, we don't just agree on, you know, what is a pebble and what is not a pebble, but we also have to agree on a, say, like a rational number which determines a reference frame. In other words, how many of my pebbles...
That last phrase got muddied. Just the last, like, 10 words got muddied.
Have to agree on a rational number to act as a reference frame. In other words, to say, oh, I have 3, you know, pieces of gold is pretty meaningless unless, for like, if I, you know, denominate my stuff in silver, unless we have a rational number which tells us how to translate between those 2 reference frames, how much gold for each unit of silver, and so forth. And, you know, the interesting thing at that stage is that, you know, like as we went sort of level by level in this sort of dialectical unfolding of the idea of number, we found that each next level provide a way of giving context or perspective to the previous level. Like I'm saying, like a rational number can give context to like an integer. In other words, by saying like, what is the relationship of the two different kinds of currencies or the two different kinds of rulers that you might use. So that was one pattern that we saw as we like went step by step. Another pattern that we saw is that very often you can sort of generalize this idea of like having a bunch of piles, a bunch of pebbles in a pile. In other words, we had a bunch of, like literally, a counting number could be interpreted as a bunch of pebbles in a pile. In the case of, when we got to having addition and multiplication, we, generalized the idea of a pebble to being a prime number. And we could look at, the number 12 as being a kind of pile where there's like a 2 and a 2 and a 3. And then we kept going, right? We then added exponentiation and root taking into the mix. And we realized, oh my God, not everything is a rational number. And we discussed, the real numbers, the square root of 2, the hypotenuse of a triangle, the square root of -1, I, complex numbers. We realized that if we want to consider the algebraic closure of the elementary operations of arithmetic, we have to, in general, consider complex numbers. And so, we could, and similarly to the idea of a rational number translating between, different notions of one, or like whatever you're denominating your quantity in, you can think of a complex number as switching a reference frame on the plane. In other words, if I have, a line that's like at 45 degrees, I can use a complex number to, and so like that would have like an irrational hypotenuse, right? I can use a complex number to like rotate it to the real axis. And, then we're good. Like, in other words, complex numbers are a way of giving context to rational numbers, just as rational numbers are ways of giving context to like integers and all the way down the line. We then wanted to generalize the idea of having a bunch of pebbles in a pile, but where the pebbles were complex numbers. And we then naturally arrived at the notion of a polynomial. Polynomial is like a pile of pebbles, but where the pebbles are complex numbers. In other words, the roots of the polynomial. And just as like there's this kind of complementary relationship between considering a whole number as being like a magnitude, like having like a certain magnitude, versus considering it as a product of primes, there's a kind of complementary relationship between the roots of the polynomial and its coefficients, right? It's like you have to actually solve the polynomial in order to find the roots, which in general can only be done with approximation. But then considering
Can only be done what? I couldn't hear.
We have to in general use, approximations to
Approximations. Oh, I didn't hear the word. I'm sorry.
Yeah. But then when we were considering polynomials as numbers, we realized, oh shit, what happens when we like divide polynomials? We have to like, if you have a polynomial over a polynomial, then the roots become poles. The roots of the denominator become places where that, what's called a rational function, go to 0. And so if we want to be consistent, we want to add, subtract, multiply, and divide our polynomials, we had to introduce the idea of a rational function or a ratio between polynomials. We then discussed like the simplest rational functions, which are the Mobius transformations. And they turned out to be the Lorentz transformations in disguise, 3 rotations and 3 boosts. And we represented those as like these rational functions like on polynomials. Then we were like, okay, well, generalizing, further, we wanted to consider, well, what gives context to polynomials? Well, it's matrices. In other words, we can look at a polynomial as a vector space. And the most intuitive way of thinking about it, it's like the different terms, the different powers of the variable act as basis vectors. And so, the idea was that with a matrix, we can switch between, looking at a vector in one basis versus looking at a vector in another basis. If we use Hermitian matrices, we have a nice feature, which is that these matrices have orthogonal eigenvectors. In other words, they fix a basis for the vector space in question. In other words, any vector can be expanded in the eigenvectors of that matrix. And furthermore, we, we're like, just as you can look at, a polynomial as like a coexistence of roots.
We have much.
The matrix as a coexistence of polynomials in the sense that, you look at, say, like a Hermitian matrix and like the basis formed by its eigenvectors, it's just a diagonal matrix. And it corresponds in a sense to a polynomial whose roots are its eigenvalues. And any given representation of that linear operator in some basis is just like that same polynomial seen from a different point of view. In other words, if you have a matrix which is similar to that diagonal matrix, then it too satisfies its characteristic polynomial. So, now we like generalize the idea of like number from pebble to, counting number to integer to rational to complex number to polynomial, and then finally to matrix. And when you get to matrices, what's interesting about it is that the rule for multiplying matrices is like non-commutative. And the important point there is that the non-commutative multiplication rule can be used to encode group multiplication rules. In other words, we have the idea of a symmetry group, and we can represent each action, each like element of the symmetry group, if we're lucky, by a matrix, by a linear transformation. And, specifically in quantum mechanics, the relevant representations that we're interested in, not just any representations, but specifically unitary representations, where we represent, in general, like continuous symmetry groups, elements of them by unitary matrices. And the point of doing this is that they can be interpreted in terms of probability and statistics. So that, the matrix exponential, which is really just the Schrodinger equation in disguise, which, in some sense describes a rotation, can also be thought of as preserving probability. In other words, if the, preserving the length of a vector of probability amplitudes, to say we're rotating it is as much to say we're preserving the fact that probability sums to 1. So once we had like all these matrices and stuff, we realized that, those Mobius transformations from before could be represented not just as little complex functions, but as these little 2x2 matrices, like the Pauli matrices. And we realized that we had sort of, almost by accident, invented the theory of quantum spin, almost from first principles. And there was a, perfectly definite, you might say, classical geometrical interpretation of a spin state in terms of a constellation of points on the sphere given by the roots of polynomial, as like we talked about today. And that, any constellation could be expanded in a basis of orthogonal constellations, and that each of these bases corresponds to a Hermitian matrix, which, at least in the case of quantum mechanics, can be interpreted as a certain experimental situation. And actually, this is kind of like if we want to continue talking about new things today, this is like one of the points I want to emphasize. So that, whereas before we, went through this whole rigmarole, we had a, if you had like a spin half state, as a 2 vector, you could take the ratio between its components, get a complex number, stereographic project it to the sphere to get an X, Y, Z point. Well, it turned out that we could get the same result by simply taking the expectation value of the spin half state with X, Y, and Z, the Pauli matrices. So that on the one hand, we have a geometrical picture, and on the other hand, we have a statistical picture. These same coordinates can be described as expectation values. In other words, a bunch of outcomes weighted by probabilities summed. And so there was like this duality, which was that like we had like a geometrical picture that at the very same time can be interpreted as statistics. And what I want to emphasize is that like, even though that's the case, you know, you don't need to care about statistics in a way when you're just considering like a single quantum system and you're like not measuring it, you're just like imagining it, you know, evolving under the Schrodinger equation. That probability interpretation, however, comes into play in a big way where we go on to the next stage. And that's where we're gonna go next, right? If we start with pebbles and go to piles and go to, you know, integers and then rationals and then complex numbers and polynomials and then matrices, what comes next? We need something that's like a kind of coexistence of matrices. And the idea that we're looking for is that of a tensor. In other words, in quantum mechanics, this is used to describe the entanglement between different quantum systems and can be seen as a series of linear maps between quantum systems. And, you know, it's in that context that we can formalize the, you know, relevance of all this stuff to actual like experiments, like where we measure things get entangled with other things. So that's like where we're going next. Yeah, so like that's sort of the grand arc, right? Like a sort of way of unfolding the mathematics which gets involved, that you get involved in with quantum physics, from as few assumptions and as simple ideas as possible. In other words, something that's very, very intuitive, which is like the idea of a pebble and what you can do to it, and slowly but surely generalizing it. And, you know, a lot of cool stuff falls out of it. In other words, you know, we find just by playing around with polynomials, we've already understood something about, you know, quantum spin, for example. And like I was saying before, that like, you know, quantum spin being the simplest really quantum system that you can imagine provides a nice testing ground for, you know, our ideas about quantum mechanics in general. And yeah, you know, like, and we'll see, you know, as we move on that like, you know, I keep emphasizing like in this lecture that like, you know, you really can interpret the quantum spin as being associated with this constellation and in some sense being just a classical system where the roots feel a force, you know, amongst themselves. And, you know, that's perfectly valid. The challenge to interpreting spin classically doesn't come from the fact that spin states can be superimposed. In fact, we've seen that a complex linear superposition of constellations is yet another constellation. There's really no mystery there. The mystery instead comes in when we consider measuring things. And measurement introduces like an entanglement between the measuring apparatus and the thing measured, and all sorts of paradoxes and fascinating things arise from there. So that's where we're gonna go next, basically. That was like a big like arc. And, you know, and eventually, you know, we're gonna get to like the idea of, like another thing we're gonna talk about is, you know, it turns out that you can represent a spin J state as 2J symmetrized spin half states. In other words, as a tensor product where the constellation's encoded like in the entanglement between the spin half particles and not just in like a single spin J particle. And, you know, then after that, like when we start talking like a little bit about quantum field theory, we'll see that, you know, this is the general form that particles take in quantum mechanics. They're, you know, always like symmetrized or anti-symmetrized. In other words, identical particles. And that idea of identical particles or identical quanta, you know, really is in a way the ultimate generalization of the idea of a pebble, which you use to count stuff. Insofar as you use a pebble to count things, like you're treating that pebble as like one pebble is indistinguishable from another pebble. And this idea of being able to treat things like as indistinguishable is sort of the basis of like atomic thought in a certain way. And so, you know, after this sort of, you know, basically the plan of action is to talk about measurement and entanglement, then the symmetrized spinor representation of spin, and then introduce quantum field theory in the context of yet another representation of a spin J state involving two harmonic oscillators, simplest quantum field theory you can imagine. And there you can see that the state is made up of, in some sense, indistinguishable quanta. And in doing that, we'll also discuss the harmonic oscillator and the harmonic oscillator coherent states. And you know, that's basically the plan. All right, that's the long arc.
Matthew?
Water off a duck's back.
What are the what?
Water off a duck's back.
Water off the what? The what?
Water off a duck's back.
Water off a duck's back?
Yeah.
Easy. He means it's
Je
easy.
ne comprends pas.
I don't even know.
Okay, Matthew, I really appreciate what you just did. This is really helpful. And I think that my suggestion is that you should, at every stage, you have to redo something like this. Maybe you can collapse. You don't have to, you can collapse going from pebbles to complex numbers next time. So you don't have to go through that part. But you do have to back up each time, as you like to say, to give things context. And I feel that to give this kind of story at the end of each of your presentations really helps us follow along and see what you're doing. And that we can follow each step, but unless you give these kind of contextualizations of what you're doing, we don't really get what you're doing.
Yeah, well, thanks for saying that. Yeah, I will definitely give some like last time on, you know, what is an atom? This is, you know, and like next time on, I'll give some, I'll make sure to bookend everything.
Yeah, it's a good idea.
Yeah, totally. Yeah, I mean, part of it is like, you know, I've been thinking so long about how to weave all this into like this one kind of story that I'm like, you know, more obsessed with like making sure each little step makes sense, you know what I mean? And sometimes I lose sight of, you know, trying to paint like the overall picture. So yes, thank you for that comment.
So,
And with that, Matthew, I think that maybe me personally, I might have had enough for today.
Yeah,
yeah,
I was just thinking like that feels like a good
good wrap up.
So yeah, next time we'll pick up here the section 8, a tensor, and I'll say this, you know, we're about to talk about, you know, some of the real conundrums, you know, like about locality and determinism. And, you know, I want to say that I recommend two things, you know, perhaps like if you guys want to do some like reading like before the next meeting, definitely take a look at that like Xavier University like transcript thing that we were talking about before. Because, you know, I finally read through it this week, and, you know, he talks about like a lot of the stuff that like has come up for us, right? So they talk about the measurement problem. They talk about like different kinds of interpretations of quantum mechanics. Hugh Everett is there, you know, talking about many.
Matthew, who was the first guy you mentioned? Xavier? Somebody?
It was Xavier University.
Oh, Xavier University.
Yeah, it was young Michael who posted this the other week, and I highly recommend reading it. You know, it's
But you're talking in terms of the Copenhagen interpretation, which again a lot of us don't accept.
Right. So what I'm saying is that in this what this was like a conference where, you know, a lot of different views were proposed. So Dirac is there, Wigner is there, Podolsky and Rosen are there.
Yeah, but David Bohm was not there.
But they
He was in exile.
They talk very respectfully of David Bohm. And they literally talk about Bohmian mechanics. They even give the equations for Bohmian mechanics, and they discuss it like whether it's like a reasonable picture, you know, of quantum mechanics.
Completely consistent with Copenhagen. It just describes it better. And again, it's the Hamilton-Jacobi formulation of Schrodinger's equation. Nothing exotic about it.
One thing that I'll say is this, like one of the points that like I was gonna make about it is that, you know, something like this, like the very reason, and they sort of mentioned this in the text, the very reason that we give up determinism is to protect locality. I can't give you a knockdown argument that says like, yes, the world is definitely indeterministic or whatever. What I can say is that, you know, I think for most physicists, it's vastly more important to protect the principle of local causation than it is to protect the principle of determinism.
The locality has already been disproven in certain physical phenomena. Entanglement is not a local phenomenon.
There's two kinds of non-locality. There's non-local causation and there's non-local correlation. So non-local causation is like literally, I can do something right here and transmit information instantaneously to a point 5 miles away. In other words, something right here can cause something to happen over there and information can be transferred.
And everybody, all theories believe in causation. All theories believe in causation, but there are phenomena that travel instantaneously, like entanglement.
Right, but no
most famous.
Can be sent.
Matthew, I think you got to be careful about this, the phrase transmission of information. I think
he's talking about causality, though.
Yeah, you might really mean what Michael's saying, which is transmission of an effect, which is different than transmission of information.
Yeah, information can only travel at the speed of light. That we know. But causality comes into every theory. Causality, there's cause and effect.
And in also, Matthew, regards to your last comment, I think that really you should look at what I take to be maybe the most impressive presentation of what you were discussing in the last 3 minutes, which is the Greenberger experiment. There's a great explanation of it in the book I keep praising, which is Malden's book, but it really shows this in a clear way how you can get tripped up and avoid getting tripped up in this distinction between locality and determinism.
Okay, yeah, I mean, I will certainly check that out. I mean, to define my terms, like I would mean, you know, the principle of local causation is something like, if you want information to be transmitted, then, you know, like in some, like in the classical ways, like things have to knock into each other. Like there has to be a chain of like, you know, something unfolding between here and there.
But it can happen instantaneously. With entanglement, it happens instantaneously.
I think probably the best way of illustrating the point is Newton. Newton's theory is perfectly deterministic, but it is not local.
Right. And entanglement, if you want to go to quantum physics, entanglement is deterministic, but not local. It happens.
Not in every interpretation, Michael.
Wait.
Sorry?
Not in every interpretation.
Can I just say?
Oh, no, entanglement. This has already been proven by Alan Aspect and Clauser. Experiments show entanglement is instantaneous.
This is such a confused conversation. Can I just say you have to be clear about distinguishing between a chain reaction and being able to control the initiation of the state of the origin of the chain reaction. Those are two different things. You can have a chain reaction. You could say, here's a physical situation in which this
Uh-oh. Hello?
initial step in the chain.
Wait, can
And
you say
what I
that again?
what
Like,
I would add to Andre, what I would add,
I didn't catch the last thing that you just said. Could you say that again?
I said that there's a distinction between having a chain reaction where one thing causes the state of the next, causes the state of the next, etc., and being able to specify what the initial state is. So when you're saying I can communicate information, a chain reaction is not enough. I also have to be able to set the an initial state so that the information I send is something I'm in control of.
also,
I
in
agree.
Bohm's theory,
Like
the quantum potential changes instantaneously.
I'm losing. What's happening?
Of particles influence each other instantaneously. There's no chain reaction as we're envisioning it. In fact, that could lead to what we would call a block universe, that everything is predetermined.
Right.
And time is our illusion.
So, like, what I'm trying to say is that I completely agree with the idea that, like, okay, a chain of causation is not enough to transmit information. You have to be able to control it in some way, control the initial state and so forth. But really, I'm emphasizing like the other side of it, which is no information can be transferred with entanglement. Zero information can be transferred with entanglement.
Well, every theory agrees.
I take exception to this point. You are right only if you try to transmit information through entanglement by measuring states. I claim that you can transmit information without measuring states, simply by comparing states.
Well,
this is a completely different way of doing it. If you try to use entanglement to transmit information, there's no way you can transmit any information whatsoever.
Okay, and picking up on what Moshe said, in quantum computing, you can transmit states instantaneously, but you can't transmit information. You've got to transmit a classical bit, which can only go at the speed of light in order to change the quantum bit, the Q bit.
I agree with that 100%. Moshe, with regard to what you just said, so what you're referring to is that parity gate that we were talking about before. But that parity gate does not just compare two quantum states arbitrarily.
Yes.
It doesn't.
Very much related to this, absolutely.
What it does is it compares, it gives you the parity in the
You're freezing up, Matthew. We can't, you're not moving on screen and we don't hear you.
Hello. Yeah, my internet was.
I think the bird flew into his window.
Oh, now I can
and
hear
took over the system.
You're sitting there as.
Hello? Oh.
The quantum system is breaking down.
He's entangled.
Uh-oh.
All right, yeah, I don't know what's going on. It never happened before.
Uh-oh. It's coming back.
Hello.
Welcome back.
Yep. Can hear you.
So what are we doing next time?
Yes. So
can we meet some women on this at this meetup site?
Yeah,
that's the only reason I'm here.
That's the one thing
who is this other Weiss? There's a female Weiss. Is she related to you?
Weiss?
She always signs up, but she never shows up.
Oh, Oh, well, that's probably my mom that you're referring to.
Oh, is
Jill.
that your mother? Okay.
Yeah.
And they're talking about the New York Times like op-ed writer Barry Weiss. Politics I do not agree with, and who just had some controversy. As far as I know, I'm not related to her. The parity gate doesn't just compare two arbitrary quantum states. The parity gate tells you, in other words, what is the parity in the Z basis. In other words, like if you have, two states that are both like up, it'll be like, oh yeah, that's parity 0, because they're the same. It'll tell you like, oh, if they're different, that's parity 1. So it only tells you if they're the same or different, like with regard to Z basis states. It doesn't just let you compare like arbitrary quantum states to each other.
Can't transmit
No,
information.
this is exactly what I'm talking about. A parity gate, exactly the way we described it. By the way, how is a parity gate implemented, where the goal is to check the parity of the two states without ever finding out what is the state of any of those particles?
So
How
it's
is this done?
that'll work. But well, wait, let me open up that thing that I wrote about the.
The point is you can't transmit information. Do you know that you can transmit a shadow? You can transmit a projection at faster than the speed of light, but you can't transmit information.
Yeah, sorry, I just want to look at that little note that I posted back a couple weeks ago about the.
How was this event?
Oh, it was the next one. Sorry. Yeah. Okay. So here, look. You look at here's like a list of like what the parity gate does. So like you see what it does is it gives you the parity, but like with regard to a certain basis, right? So like if A and B are just in like basis states of Z, say, then 0, 0, and 1, 1 give you, that's their even parity, and 0, 1, and 1, 0 are odd parity. And so, the idea was like you have 3 qubits, you're interested in A and B, and C is an auxiliary qubit that starts in the 0 state. And you can implement it with 2 C naughts. And the idea is that when you go look at C, it'll be 0 if the parity is even and 1 if the parity is odd. And then you can see that like, these are each, the separable states. But, if you look at the entanglement, like it still works. Like if you have 0, 0 plus 1, 1, then C gives you, that. It's an even parity. And these are both odd parity. But, if these were just like arbitrary linear combinations, then, like for example, like what would it give you if instead you had like the XX state, instead of 0, 0? Then this gate like would not give you the parity of that.
But you're not transmitting information. That's the bottom line.
Matthew, I'm interested in a somewhat different comparison of 2 states.
Okay.
I want to compare the state of, let's say, 2 electrons. I know that 1 electron, I know for sure that it is in a superposition of up and down, let's say in the Z direction. The other electron, I'm not sure. It may be in a superposition of up and down, in which case both of them are in the same state, or the other electron can be in a pure state, either up or down. I don't know if it is up, I don't know if it is down, but what I want to know is,
Moshe,
one moment.
wrong.
What I want,
50-50. It's not any superposition, it's 50-50.
okay, fine. What I want to know is, are those two electrons in the same state or not? Are both of them in a superposition state, or is one of them in a superposition state and another one in an eigenstate? Is there any way I can have this kind of comparison done?
But Moshe, you're not transmitting information.
Let's see.
Let Matthew.
Let Matthew answer.
Well, actually, you guys talk for a second. Let me code something up really quick. Like,
You know, in quantum computing, you have a teleporting, it's an unfortunate name. You can teleport a quantum bit faster than the speed of light. But you can't teleport information. You still have to send a classical bit at slower than the speed of light to teleport this quantum bit. And it involves a C0 and a combination of C0 and Hadamard gates. Bottom line, you cannot transmit information at faster than the speed of light. There's lots of things you can do faster than the speed of light. You can do error correction, all these other things. You can't transmit information.
I agree. Yeah, my point before was something like, arguably it's the indeterminism that makes it so that you can't transmit information with entanglement.
We don't believe in indeterminism. Bohmian mechanics is deterministic.
Right, but so consider the classic argument, right? It's like, which I'm sure you know, right? Which is like, if you have an anti-symmetric state, Alice measures along the z-axis and gets up. And if Bob measures, also along the z-axis, he'll get down. And so you could naively think that, the particles had agreed on something beforehand, but what if Alice had measured along the x-axis and had gotten, sideways? Then if Bob does a z measurement, he'll get up or down half the time. And so, the two particles couldn't have agreed on what their spin was beforehand because what they give depends on Alice's choice on what to measure. But, even though there's this non-local correlation, this doesn't mean that information can be non-locally transferred because, even if Alice just sticks to measure along the z-axis, each time the answer is random. It's like up or down, up or down.
This is clear. This is clear. This is something that you're all familiar with, that there's no way you can transmit information this way by measuring states. Measuring states will not get you anywhere. I'm talking about something completely different. I'm talking about comparing states. And I don't want to compare two states where both of them are up or one is up and one down. I want to compare two states where one of them is a superposition of up and down, a linear superposition, 50-50, up and down. The other one, I don't know. The other one may be a superposition of up and down, or it may be a pure state. I want to compare those two. Are those two electrons or those two qubits, are they in the same state or not? That's all. I don't care at all about the actual state. If one of them is in a pure state, I couldn't care less if the pure state is up or down. All I want to know, this state is different from the one that is a superposition state.
And Moshe, will this enable you to transmit information?
Yeah.
It will?
Yeah, this will
How
enable
so?
me to. This will enable me to transmit information instantaneously. I could not transmit information from the past to the future or from the future to the past. But I could transmit information instantaneously from here to 10 million light years away.
Yeah, I think you might be out of luck, Moshe. You might be out of luck, Moshe. I say that because, so here's a little piece of code I wrote. So this does the parity gate. In other words, A and B are each C0 gates, and that's how you build the parity gate. I start with an initial state, which as you say, it's like a superposition between up and down.
Okay.
So that's what this is here, 1, 1. And then I just choose some random other state. And then I tensor them together. And then I apply the parity gate. And then the answer should come up for C, like the other qubit. And you see, every time I do this for C, I always get the maximally mixed state. Right here. So if you just do your parity gate and you start with a tensor product of a superposition up and down, and then just like any old random state, then every time the parity gate will give you a maximally mixed state on the output qubit.
Regardless of the
Really,
actual
that
state.
means just basically you can't do what you're saying. I'm sorry. I wish.
Well, not with CNOT parity gate. This is not going to do the trick. Basically, because the CNOT does measure the state.
I mean, it's a unitary operator, so.
Matthew, can I again suggest that we continue on next time? This is really going on.
Okay, yeah, let's do it. Unless there's any other points of order, we shall meet either next week or the next. Moshe, let me know if you come up with a interesting kind of parity gate, and I will write the code to test it and see. Because
I'm looking for help, Matthew. I'm looking for help from you. You're the expert in this field.
Okay.
I know what it is that I want to accomplish. I want to be able to compare a superposition state with a pure state. I want to be able to distinguish, to tell if this state is a superposition or a pure state. What the state is it up or is it down? I couldn't care less. I'm not interested.
Okay. I'll think about it.
If anyone can come up with any hint as how to approach this problem, this would be great.
Yeah, no, that's what we're thinking about.
Okay.
Because it gets at the idea of like, can we make a distinction in general between basis states and superpositions? It's not clear to me that we can, like as I say, but it would be interesting if it were possible in some situation. Cool. Well, until next time, thank you all again for coming out.
Okay, thanks, Matthew.
Yeah, thanks.
See you guys.
Okay, bye-bye.
Bye.
Bye.
I never know how to end this thing.